Hello, we continue with the previous lecture when we discussed mechanical advantage issues in compliant mechanisms. Today we will quickly review what we discussed in the last lecture and then discuss some what can be called advanced concepts with mechanical advantage relating to compliant mechanisms. So, this is the lecture number 54. So, we were talking about mechanical advantage and there is a formula that we took from this paper of 1998 from Solomon and Medha. So, where they gave the formula for mechanical advantage, where I have conveniently color coded here. The blue one is the kinematic part or what we can call rigid part, and then the red one is the compliant part or the elastic part. So, mechanical advantage of compliant mechanisms is a rigid or kinematic part, compliant or the elastic part, two parts are there, and the definition of course is output force divided by input force, that is the mechanical advantage for compliant mechanisms, because they have inherently some kinematics in them. Intrinsically there is some kinematic behavior which is captured as in fact this is delta u in by delta u out, not u in by u out, that is incremental change in the displacement divided by incremental change in the output displacement, that is input and output, that is the rigid or kinematic part. The other one including the minus sign, that is something that we need to notice, including the minus sign, that part is MAC, the compliant or the elastic part. Delta change in strain energy, this is also delta, that if you refer to the previous lecture is delta u out, and then F in input force. So, this is the mechanical advantage formula that we have, and we also discussed that there are three types of mechanical advantage one can define depending on what we are fixing. So, that we have the effect of input force and displacement, output force and displacement, and most importantly the workpiece stiffness, because depending on the stiffness of the workpiece, that is the object which we are going to apply force onto, the mechanical advantage actually changes for compliant mechanisms, because their kinematics is affected by the forces, because there is elasticity in them, whereas rigid linkages or rigid mechanisms if you take, their kinematics is not altered by the forces. But in compliant mechanisms, since there are elastic members, the forces, the input force, output force influence the kinematics, inherent kinematics of the mechanism, and hence mechanical advantage actually changes, and that is what we are discussing. Both MAR and MAC would change depending on the elastic component, because this incremental displacement delta u in delta u out are changed by the forces. So, we have to consider the effect of stiffness of the workpiece, and for that there was this sensitivity coefficient, that is sigma, as defined in the paper by Solomon and Medha, where you use symbol sigma. In our notation we have this as S, and Kw is K external, that is workpiece stiffness. What we are talking about, stiffness of the workpiece is here. How sensitive the mechanical advantage of mechanism is given by this sigma. If sigma is 0, then we just have what is known as bounding value of the mechanical advantage MAS, because then it will become 1 when sigma is equal to 0. So, our aim is to make sigma as small as possible. Now, one other point we need to remember is that the compliant part of mechanical advantage is negative, because there is a negative sign here. Including the negative sign, we are calling that MAC. So, delta SC is there and delta out and F in with a negative sign is MAC. So, what this formula tells you is that mechanical advantage of a compliant mechanism is actually hindered by the compliant component, because rigid body component or kinematic component is simply the inherent kinematics there, delta u in by delta u out, right. So, now to that one you are adding a negative quantity, adding meaning we have put a plus sign here, adding a negative quantity which is MESC. So, from the viewpoint of mechanical advantage, there is actually a disadvantage for compliant mechanisms. That is clear because part of the input force and hence energy is used to deform the mechanism. So, there is like a cut taken here as compared to rigid body linkages, and hence both mechanical efficiency as well as advantage are affected when we have this. And then in the last lecture we had said, is there a way to overcome this, and I am going to discuss that now. How do you make that disadvantage disappear? That is, mechanical advantage of compliant mechanisms, can it be more than the kinematic or the rigid body part, that is more than this blue part. And the way to do this is make that delta SE negative, because in that formula minus delta SE divided by delta U out F in. F in direction we cannot change, that is the input force, and incremental change in displacement, it should be in the desired direction. So, delta U in also cannot be negative. Then what can be negative is delta SE, the change in strain energy. Okay. To illustrate that, I am taking a simple example. It also will be an illustrative example to see how we can evaluate or derive the mechanical advantage formula for a given compliant mechanism. This simple compliant mechanism which is fixed at the bottom here, and there is F in here, it is a symmetric one. So, there is F in on both sides, you press like this and the top one goes up. So, the output displacement here, so when we press like this, it should go U out, and F out can be here, U out is shown with an arrow, that is to see that F out is in that direction, that is not U out. F out will be resisting the output displacement downwards, that is this way, and U out is going up. So, such a compliant mechanism, here we have taken something simple where there are these flexural pivots, which is not a great thing, but for an example we have taken this. So, for this we can make a model, that is I can take the symmetry. So, I have symmetric axis this way and that way, I can take only this portion. If I take only that quarter, then I can show that there is some K in here, there is a translational stiffness and there is also a rotational stiffness here, that is kappa 1. Similarly, there is a kappa 2 here, and then there is our K external. K external is like workpiece. So, we are acting against that, okay, or towards it, whichever way you look at. So, this is the model for that, and once you have the model, we can write the displacement. So, if I call the distance from here to here as A and then here to here as B. So, A equal to, this is L, this is theta, the angle. So, A is L cosine theta. If I want delta A, that is going to be my delta U in, how much when I apply input force in that direction, how much does it displace? We have to take that dA by d theta into delta theta to first order. This is an approximation, right, dA by d theta into delta theta, first order term in the Taylor series, and dA by A is equal to L cosine theta. So, dA by d theta is minus L sin theta, because A equal to L cosine theta times delta theta will give you delta U in. Similarly, when I have B, that is this here, that is L sin theta, delta B will be my delta U out, the incremental output displacement, that is dB by d theta delta theta. Since B is L sin theta, dB by d theta is L cosine theta. So, this is L cosine theta delta theta. So, now we have delta U in by delta U out. So, kinematic component delta U in by delta U out is minus L sin theta delta theta divided by L cosine theta delta theta. Delta theta get cancelled. So, LL gets cancelled, it will become minus tan theta. That is the rigid body component or kinematic component. So, that is what we get. This is actually MAR, it will be minus tan theta. And then we have this formula for these, right. So, which also has the compliant component. For that we need to write the strain energy. We write the strain energy for this, the K in this spring times delta U in square, that is the incremental displacement in that, and then this spring that has delta U out square, for which we have the expressions, these two, and then we have kappa 1 times theta minus theta naught square. There will be one position which is the free state of the torsion spring, that is denoted by this theta naught for both springs, that is kappa 1, which is over here, and then kappa 2 which is over there. There is some free state for it with theta naught, and then when it displaces to another angle theta, theta minus theta naught square will be the strain energy in that, multiplied by kappa 1 and then half of that, and then likewise the last term as well. So, we have SE. If I want to get delta SE, I need to know the derivative. So, dsc by d theta, you take the derivative with respect to theta, we get this, and then I can write delta SE dsc by d theta times delta theta. Once I have this, I can go here again, the deltas are missing, cut and paste, if you miss one place that missed everywhere. So, delta U in by delta U out, we have those. So, delta U in delta U out we have. Now, we have delta SE as well. If you do that, you will get the blue part, which is the kinematic part, you get the compliant part. Again compliant part delta SE, if you see, you have to look at this term. So, dsc by d theta into delta theta. If you say delta theta is positive, then you have to look at these expressions to see if there is a chance for them to become negative, because unless delta SE is negative, we are not going to have a positive contribution towards the total mechanical advantage, because MAR will be what it is, and then we have to plus add something positive. So, MAC has to be that can be positive along with this negative sign here. It is possible only if this is less than 0, that is what we want. Okay. That we have to look at this dsc by d theta, that is what will be controlling the sign of it, because luckily we have minus k external L square cosine theta sin theta. So, wherever this becomes, let us say positive, and then it depends on the relative values of k in and k external, and then we have kappa 1 and kappa 2, one of them has minus, another is plus sign. Overall we have to see how they have all become positive or negative, but at least it gives a hope that for some parameters of k in, k external, kappa 1, kappa 2, you can make delta SE negative for part of the motion of this device. If you do that, you get a mechanical advantage that is actually more than the kinematic part, or what we call rigid part. Okay, that is the idea. We have to make delta SE negative, meaning strain energy of the device should decrease as you deform it. That is counterintuitive, because whenever something deforms, we know that strain energy is going to increase because there is deformation. So, how do you make it decrease? Before we discuss that, let us look at for this example with some parameters, we are able to get that this is the total mechanical advantage, this is MAR, this is MAC. You can see that in this particular case MAC is positive, because as you can see here, this is MAR, that is very little here, this is MAC. Total mechanical advantage of course is more than the rigid body one, that is dashed line. Above that we have the dotted line, which is overall advantage, because it is positive for a long range, that is from 0 to about 55 degrees of the angle here, it is positive. After that it goes negative, which I have not shown here, but the point is that we can actually design compliant mechanisms where we can have the compliant component positive for the mechanical advantage. Okay. That is the point here, that we need to have the strain energy, delta strain energy should be negative. Strain energy cannot be negative, but delta strain energy can be negative, or rate of change of strain energy with respect to the state variable of the device, that is one particular variable, degree of freedom you can call it, that should be decreasing. Okay. then it is possible, and that is exactly what is shown here. So, strain energy here should be decreasing as you deform the mechanism. Okay. So, in that case mechanical advantage can be greater than the rigid body or kinematic component of the mechanical advantage of the compliant mechanism. So, how do we do that? How do you make strain energy decrease as you deform the mechanism? Again I emphasize that this is non-intuitive. Whenever you deform something, you think, or it is actually you correctly would think that strain energy will increase, but how do you make it decrease? So, one way is to have a compliant mechanism that has snap through or bistability. Another way is to have preload in the compliant mechanism, that is you put in some strain energy to begin with and design the mechanism in such a way that when it deforms, instead of it taking energy from the input force, it will take from the stored energy. That is, you give compliant mechanism a savings deposit, that is it will have the saved energy in it preloaded, it will take that to deform, and then whatever input force or input energy you are putting in, that will be used to serve the output needs. That is the principle here. So, you need to have snap through or bistable. Usually these things also can be done with preload or without preload. So, if I say this is one, I would say another is preload, that is you save some energy into the mechanism when assembling the mechanism itself. A compliant mechanism will always have some fixed points. So, you move the fixed points so that forcibly they are tightened and fixed to a frame, so that there is some energy without any external forces acting. If you do that, that means there is a preload, that means there already is some strain energy in the mechanism. Now, when you move it, it will use its own energy to deform rather than using additional energy. For that you have to carefully design the compliant mechanism, that is the way it would move would make it possible for the mechanism to use the energy that is stored. Okay, just about anything you design may not work that way, you have to do it carefully. That one simple example that we just discussed enables you to do that. You can preload it and then use that energy to come. We will be discussing this bistable phenomena in compliant mechanisms in the next few lectures, next 3 lectures actually. So, another point about mechanical advantage, we are switching gears now. We also discussed that if we use spring lever model, we can get some insight. This is what we had discussed in the last lecture. We just reiterating that this mechanical advantage has a bounding component, and then there is a sensitivity coefficient to the K external, that is the workpiece stiffness, that is in 2 places. This is the workpiece. So, workpiece has some stiffness. It is nice if you have a compliant mechanism whose mechanical advantage does not depend on the workpiece stiffness. It is nice to have, right, because you do not have to design one for handling very flexible objects, one for rigid objects. So, if you want to have one mechanism that works for several or a large range of workpiece stiffness, that will be good. For that you have to make sure that this Sk is small. If it is 0, that is ideal, otherwise you make it as small as possible. The spring lever model, where we have this lever ratio n and there is input side stiffness Kci, output side stiffness Kco, these 3 parameters, how do they influence this bounding mechanical advantage, that is asymptotically goes there, right. When K external keeps on increasing, then Sk becomes irrelevant, then it becomes 1, so you get to MEIS. So, it just goes asymptotically. So, what influences? We have the formula here, N, Kco, Kci influence, all 3 parameters influence. How they influence also is here, and then what influences Sk is also here, and the relation between MEIS and Sk is also here. So, our aim is to make MEIS, rather bounding mechanical advantage, as large as possible. At the same time we want to make the sensitivity as low as possible, and between them there is a relationship MEIS and Sk. If we say that we want to optimize, so that I want to maximize MAS by Sk, then it amounts to maximizing n by Kci, because MAS by Sk is that, because I want to maximize MAS, minimize Sk, so I put in the denominator. So, I have to make n by Kci. It is not as simple, because MAS also depends on KCO, as we see in this formula. Okay, it is all interrelated. We had discussed optimization problems here, that, but SL model, spring-lever model, gives you an idea of designing a compliant mechanism in view of mechanical advantage also throughout the motion, because these three parameters KCO, n and KCI change from position to position. So, if you can determine them, which we had discussed earlier, we will also know how mechanical advantage changes our compliant mechanism. Okay. These are the things that are not accounted for when you do the synthesis the way we have discussed, because those synthesis techniques mostly focus on the functionality, that is the direction input force moves, input displacement happens, and then how output force, output displacement do. That is what we have discussed. But now it is a finer point of mechanical advantage, which also can be accounted for with these spring lever model parameters. We will also now discuss the non-dimensional portrayal, which we had discussed earlier. In general, how to use this as a design technique. So, as our fourth design technique, non-dimensional maps, which you had called kineto-elastostatic maps and kineto-elastic maps. Now, we discuss for a few minutes how we can actually use mechanical advantage also and portray it in a non-dimensional fashion. This is the work done by one project assistant in my group, R. Gautam, and Mohit Mathur, who was a MTech student at IISc. It is their work. So, what is shown here is that mechanical advantage, which is on the y axis, it is non-dimensional, because F out by F in, output force by input force, has no dimension. And then we have here eta in. Eta, if you remember from the lectures on non-dimensionalization of compliant mechanism performance parameters, was F S square by E B D. F here is taken as F input for some fixed output. If you think about mechanical advantage type 1, type 2, type 3, either output displacement or force are fixed. Here output force is fixed, in that is also non-dimensional fashion. Eta out is 0.1, eta in is here, where that becomes F in, that becomes eta in. If that is F out, it becomes eta out. And what is shown here is for different sizes, right, the scaled 0.5:1, 0.75, 1.5, 2:1, and then there is a original scale. They all lie on a curve. That is what we had said, that they will all lie on a curve. This is for this mechanism, a compliant gripper, they all lie on a curve. We can see how mechanical advantage changes. In fact, here it is 0.8, meaning that it is actually not an advantage. F out is smaller. If it is mechanical advantage is smaller than 1, F out is smaller than F in, it is not really an advantage, but just to show that we can actually do it against this. Then, as we have discussed, once you have this curve, there will be an S value, slenderness ratio for it, and for that value it is fixed. We can draw it for different S values as well. And this is here where we have taken it for particular output stiffness. Again, for this mechanism, we have drawn this for different scales. How it goes here? Here we have input force fixed, whereas output force is varied. So, what we have here is actually eta out. So, this is how the mechanical advantage changes with eta out. So, output force here, input force is fixed. Previous one was that, because there are parameters as we saw, that is why it is necessary to define different mechanical advantage depending on what is fixed. Here is one that is drawn for different slenderness ratios. So, again it goes from 8.7 to 35. In fact, anything less than 10 one should question it, but 8.7 is close enough to 10. So, how mechanical advantage changes, goes up to 10 here, and again output force is specified here. If you change that, the curves will change. So, you have to draw all of these for different parameters, but most importantly for slenderness ratio, S here is slenderness ratio. You have drawn that, so we can see what happens. Okay. And on the x axis we have eta n because output is fixed. And when you have these plots, now this is drawn for two different mechanisms, and of course this goes up to 10, this goes up to 20, and different S values here. Again 4.3, 5.7 should be actually discounted, but they are just drawn here. So, if you look at them, you can see how the mechanical advantage changes with eta in, which basically has the input force. See how it changes for fixed output force. You have to draw it for different output forces as well, and also K external, that is workpiece stiffness. You can do that, and looking at it, you can see how your mechanical advantage changes, and you can choose the appropriate range for you to work with. So, non-dimensional one, once you have, if you want to use this mechanism or this mechanism, you want to further decide, let us say that this mechanism already satisfies your kinematic requirements or functional requirements. Now, you want to go to the next level, that is mechanical advantage wise, is it helpful or not. In order to do that, if you have these charts, you can quickly assess what mechanical advantage you get, right. So, that is how these charts can be used, and you can compare different compliant mechanisms as it is shown here. So, we have a database of 85 mechanisms. If we have these charts for all of them, these are kinetoelastic maps here. So, we can also wonder about how the mechanical advantage changes, which one to choose. So, sometimes as we had already discussed, mechanical advantage can have a peak, a maximum, and you can see at what value of this eta, and it is S equal to 170 here. You can do it for different SS also, as it is done for this mechanism. S equal to 22, 16, 9.5, it is done. Okay. If you have this, you can actually compare and then see what you want to choose and where you want to operate, that is where do you want to apply the force, what range of input force, where you get the most mechanical advantage. You can design, because non-dimensional, you can adjust your size and other things to operate here, because that is where the mechanical advantage is largest. You can actually operate your mechanism in that appropriate range, and you can do it for different slenderness ratios as we had already discussed. So, it goes from 34, 42, 56.67 and 85 and 70. You can look at all these and then what you get, and you can see that it kind of tapers off as you increase the value of eta, meaning that force as you apply. You can apply the force in this case, this input force is like that, and then output force is like that. This is the output, this is the input. We can see how mechanical advantage changes, right. So, all that you get from non-dimensional, you can resize it, change material, whatever, because it is non-dimensional. And you can also non-dimensionalize the gap. The gap here in this particular one is this. Let us say this is the gap. Let us say there is a little object, okay, which is not touching, not fitting in between the two edges here. Then you have to see for different gaps how does it work. Then you can see how that changes, mechanical advantage changes based on the gap. So, the gap is increasing like that, okay, because the red one is 0.0058 non-dimensional. G, the gap divided by the characteristic length of the mechanism, and then goes all the way down. So, actually gap, this is 0.2. So, gap actually increases this way, gap increases that way. We can see how mechanical advantage changes. If gap increases, it is mechanical advantage is decreasing with eta, meaning that has F in. So, how that changes, apply more and more force, it goes there, there is a maximum for all of them somewhere, okay, and then it decreases also at a less steep rate. Initially it increases much sharply, then it decreases afterwards. The other thing that will be helpful in designing from the viewpoint of mechanical advantage. And you can also do it for different workpiece stiffnesses. Right now it is shown as absolute, but that can also be non-dimensionalized, so that you can use the same chart for many more situations than specific values of workpiece like that 5 Newton per meter square, or actually it should be K. So, they should be only that, not meter square, Newton per millimeter. Okay. So, we can also look at this for again not square, that is a mistake. Workpiece stiffness you can draw for different mechanisms and choose the mechanism that you would want to use. So, the main points are that how to obtain mechanical advantage for a given compliant mechanism. We discussed with a simple example in this lecture, and then we also discussed how to make mechanical advantage of a compliant mechanism larger than the kinematic part, that is MAR, what is the rigid part, that can be done with preload or bistable mechanism. So, basically there should be a negative stiffness for some region, that is when strain energy can actually decrease. It can never be negative, but it can decrease with the deformation of the mechanism. And we also discussed a non-dimensional portrayal or depiction of mechanical advantage, so that we can compare different compliant mechanisms and choose the one that suits our purpose, not just from functional requirements, but also for mechanical advantage requirements, because mechanical advantage is more like a secondary thing. First you have to have a mechanism that serves the purpose of the function that is intended to. After that it is a luxury, and you want to have it a mechanical advantage. But if you think about it, compliant mechanisms or rigid body mechanisms, mechanical advantage is a very important characteristic, but design method we have discussed do not directly address that. That is what we need to remember, that is what we talked about in this lecture. Thank you.